Hi, this is a video on the application of the linear impulse momentum method of kinetics. Okay, the linear impulse momentum method is nothing more than a form of Newton's second law, where the acceleration term is split out to be delta v and delta t. And the left side is force times delta t. That's the impulse term. And the mass times velocity is the momentum term. So this is literally called impulse. It's called momentum. Okay. It's one of three methods in kinetics. The other methods in kinetics are work and energy method, and dynamic equilibrium. And any of the three methods works just fine to analyze a system involving mass and motion of the mass, i.e., dynamics. But it depends what you have as known values entering the question. In impulse momentum, if you know the time and the velocity, and perhaps you want to know the force or something, those three are unknowns. The mass will be known. The mass, you're going to know the mass of an object. But of the four different values here, the performance metrics are velocity and time. The force is typically an applied force, a thrust force from an engine, or a braking force from a braking system, a drag chute or something. And mass, of course, is a property of the object. Okay, so it's well suited to situations where you are eager or otherwise interested in knowing the time or the velocity. Okay, but there's other forms, other measures of performance, and they are acceleration and displacement. This method doesn't address those directly. It doesn't have anything. You can't get acceleration or displacement out of it. You can only get time or velocity. If you happen to have inputs that align more closely with the kinetic method called dynamic equilibrium, in which case you have acceleration, that may be a better fit. Likewise, if you have a problem or a collection of data that includes velocity and displacement, but not time and acceleration, then the energy method is a nice fit, because its currency is displacement and velocity. Now you think to yourself, well, that's great, but what if I have these inputs, displacement and velocity, and I want acceleration? Right? Well, the link to all that is kinematic analysis, which is the equations of linear motion. Okay. In other words, if you have a problem and the initial data you have is time and velocity and applied force perhaps, go ahead and work the problem using impulse momentum method, obtain the unknown, time or velocity, or maybe force, but time or velocity, and then follow up with kinematics if you want to know displacement or acceleration. Similarly, if you have in your initial data acquisition velocity and displacement, then the work energy method is a nice easy fit. So use that method and obtain an unknown, or the final velocity or the final displacement. And then you say, yeah, I'd sure like to know the time. You don't have to go to the impulse momentum method. You've already applied kinetics. You've applied it in the form of the work energy method. If you need to have time out of this, then take your output from the work and energy method and use the kinematic equation and get your secondary value you want. Okay. All right, back to the impulse momentum. Linear. I'll do angular in a different video. Linear. It's a very simple little equation. It's a one-liner. Force times delta t is mass times delta v. The deltas just mean delta anything is final value minus initial. So this is force times t final minus t initial. Mass times v final minus v initial. Often, the initial velocity, initial time are taken to be 0. So those become simpler calculations. But it's a simple little calculation. The devil's in the details. This you can't just say, here's the equation and off you go then. It's in applying it. It's to just take that equation and say just apply the equation. Well, that's the whole difficulty. That's like rolling up a TIG welder outfit to somebody and saying, well, here's a TIG welder and here's a bunch of aluminum, and yeah, this welder sticks that aluminum together, so here you go. Just make lightning with this, and good luck. Obviously, you'd be the world's worst TIG welder. So here we go. Let's demonstrate how to apply the impulse momentum equation. I'm going to do a few examples. The first one is going to be a passenger elevator, and we just happen to have data, we just happen to have input values that align well with the impulse momentum method. So a 1,500 kilogram elevator is subject to a lifting force of 16,000 newtons. Now that could be a cylinder force, a hydraulic cylinder force, or it could be a cable, more likely a cable tension on a cable drum. Okay, but 16,000 newtons acting on this elevator. Okay, how long will it take the elevator to reach V equals 1 meter per second? You know, you can't, it's not instantaneous. Nothing accelerates instantaneously except light or something, which has no mass and is bizarre. But okay, if you could accelerate instantaneously, you wouldn't want to put any passengers in there because they'd be turned into primordial mush, you know. So thankfully there's an acceleration happening here. But I'm not going to be able to tell. I didn't ask that question. I don't want to know it. Right? In fact, here's what we know. And it doesn't hurt to put the little grocery list like this together. Mass 1,500 kilograms. Force 16,000 newtons. V final 1 meter per second. Okay, required to find time t in seconds. Okay. Well, to the surprise of nobody, since this is a video on linear impulse momentum, these unknowns or these values, mass, velocity, force, and time, are a direct bullseye on the impulse momentum equation here. Okay, and you think, great, I'll just plug in the numbers. The problem is, and you have to recognize this, the 16,000 Newton force is not purely devoted to acceleration. The 16,000 Newton force does not all go to acceleration. And you're thinking, what do you mean? Sure it does. Not really. Now, you don't need a free body for this, but it doesn't hurt. Free body diagram of elevator. Okay. The elevator has weight, and it opposes acceleration, or mass opposes acceleration. In a free body, we don't put mass, we put weight. So here's 16,000 newtons, sure, but the weight is 1,500 kilograms times 9.81 meter per second squared. The weight is, right, 14,715. 14,715 newtons. The net force, so that's the gall darn thing, hey? There you go. Yeah, sure, this times that, but what force do we have? The net acceleration force is only, well, 16,000 less 14,715. Okay? 1,285 newtons. All right. Okay, so F delta T is M delta V. Applied force, force to accelerate. This is the force that's causing acceleration. Very important distinction. 1,285 newtons. Delta T is the unknown. Mass 1,500 kilograms. Delta V, well, final V is 1 meter per second. Initial V is 0. Unnecessary to do that, but okay. T equals, initial T is also 0. T equals, well, 1285 invert times 1,500. And out pops the answer, 1.17 seconds. 1.17 seconds. I wouldn't take that to 2 decimals in reality. You know, if you actually measure the thing, it would be, well, 1.2 would be reasonable, okay? That's impulse momentum. the units are, pardon me, the units are weird. Newton seconds for impulse and kilogram meter per second for momentum. It doesn't really matter what the units are, but seconds do fall out of there quite nicely. The unit analysis, not a bad thing to look at. But just, I just slammed the units in there, but let's have a look at the unit analysis. Here it is here, unit analysis. Okay. F delta T is M delta V. Okay. You can't say something equals something else unless the units are the same. You can't say, oh, these crate of apples equals that crate of oranges. You cannot do that. So force, units for force, newtons. Units for time, seconds, obviously. There's the units for impulse, newton second. Mass, units, kilogram. Velocity, units, meters per second. And they go, oh my golly, it's not the same. Well, hang on a second. Newton is a kilogram meter per second squared. You should know that, okay? Come on. And that's kilograms. So we get rid of the newtons, and right? And you can see, hey, happy days. This second cancels, that goes to exponent 1, and sure as heck the units are the same, okay? The same approach works with US customary. You got that ugly unit of mass, the slug, pound second square per foot to deal with, but the same analysis works, okay? So I didn't show that initially, but now if you wanted to know the acceleration of this thing, you could take that, I spoke about acceleration being infinite and crushing people to death, but it's not infinite. But is it 1g? 1g of acceleration. If an elevator accelerated at 1g, people would be crumpled to the floor because it'd be the doubling of their body weight. That's how they'd sense it. A 150-pound person would suddenly feel like they weighed 300 pounds. Okay, so you might want to check the acceleration. Well, you just roll into here and you just use one of the, this right here. That would work. Right there. V final equals V initial plus AT. In fact, go ahead and do it. As an adder. Acceleration. Don't. It's not 9.81. That's no. This thing's not in free fall. It's a machine. The acceleration's subject to the mechanics of the machine, the gear ratio, and so on. Acceleration. Use kinematics. V final equals V initial, and same thing. You just go shopping for an equation that lines up nicely. V final is 1 meter per second. V initial is 0. Acceleration is unknown. Time is 1.17 seconds. Acceleration equals 1 divided by 1.17. Whoops. 0.855 meters per second squared. So, what does that mean? Well, gravity is 9.81, so this is not even a tenth of a g. It's a very gentle acceleration. Gravity, again, 9.81. 1g of acceleration, again, if the elevator accelerated at 1g. Well, it'd be exciting. It'd be a carnival ride is what it would be. Okay. Anyways, that's the first one. Let's try another one now. Okay. Now this one's kind of cool. This one. Now I don't know if you're into model rocket engines. I used to be. They're hella fun, as you young folk would say. But there's a model rocket engine here. Model rocket engine example. Okay. A company called Estes. Estes C6-5 rocket engine, rocket motor. You look it up, and right on the Estes website, it tells you the data for it. It says, oh yeah, it's a 10 Newton second impulse. 10 Newton second impulse. Well, hey, hang on a second here. That's literally not. It's not the force or the time. It's the impulse. It's Newton second. It's the left hand side of the equation. It's that. So right off the website for the rocket engine company, the impulse is given. Okay. Required to find. Okay. Final velocity. And I'm going to say theoretical. More about that in a minute. Of a model rocket with mass of 70 grams. Estey's website says the design maximum mass for that engine is 104 ounces, which is 120 grams or something. So, okay. All right. Well, here's what we know, right? Mass, don't be fighting with grams. 0.07 kilograms, right? Divide by 1,000. Okay. F delta T is 10 Newton seconds. RTF, V final in meters per second. Why meters per second? Because that's what's going to spit out of the equation. That's why. We can always convert it to something more exciting after the fact. But so here we go. F delta T equals M delta V. Again, it's a direct hit, right? We've got 3 of the 4 values. F delta T, 10 Newton seconds. Mass, 0.07 kilograms. Unknown is velocity. Velocity equals, well, very cool, 10 divided by 0.07. 142.9 meters per second. Now, have you ever seen one of these rockets? I don't know if it goes 142. In fact, it won't. That's why it's a theoretical, because at extreme velocities or even moderate velocities, like baseball pitching speed and so on, the effective air drag is significant. Drag scales with the square velocity. So if you have the previous one with the elevator didn't mention anything about drag because it's only 1 meter per second. The air resistance drag is negligible. But with this one, there's a whole other, imagine the drag. You square that. Oh my God. And then multiply it by, I forget. But it's going to be pretty brutal. So this is theoretical. But anyways, in kilometers per hour, I got a handy dandy converter here. Let's go speed, meters per second. 514 kilometers per hour. Now, if you've ever seen one of these rockets, nothing moves faster, than a common person. Well, a bullet, I guess. But okay, that's a quick little thing on a rocket engine. The actual, because of drag, I'd estimate the actual velocity to be somewhere, below 400, but we're not going there in this class. So in this instance about drag, okay. All right, let's try one more here. This is a question out of a technology textbook. I'm going to modify it, but example, okay. And here it is. It's an 80 kilogram mass, and it's sitting on a surface. And this coefficient of kinetic friction, mu k, is known, 0.7, which is pretty high. There's whatever it is, but it's a wooden crate on a wooden floor or something. Okay, and you're pushing on it. Something's pushing on it. 680 newtons. And that angle is known, 1518 slope, 15.8 and 17 is a slope triangle, okay? And so you're trying to move the thing, okay? Required to find, okay? Final velocity after t equals 3 seconds. Final, or just velocity, but final velocity of crate at t equals 3 seconds. Now the question I'm basing this on, t is 7 seconds, and it's like, okay, I'm going to push this crate across the warehouse, and in 7 seconds I'm going to be going, 80 miles per hour. So it's ridiculous. So I made it 3 seconds. That's the modification. If you can find this question in a textbook, more power to you. But okay, let's do a little known thing here. Well, mass is 80 kilograms. Right? Now, force is, I'm not going to go there quite yet. T is 3 seconds. Okay, those two are easy. T is 3 seconds. In the impulse momentum method, we got F delta T, M delta V. So M is known, T is known, V is to be found, and the question is force. And just like the elevator question, accelerative force, i.e. net force. The force over and above what constitutes equilibrium. You learned that in statics. You said, oh, this force, that force, the thing's not moving. It's in static equilibrium. There's no acceleration. Well, we're not in that anymore. We're not going to have anything to analyze if the thing's in equilibrium. The point is, we have a force imbalance, and the net force is going to cause acceleration. So it's not known right here. So we have to initially perform a little bit of, well, we have to do a free body. And you think, I don't want to do a free body. Okay, we won't. Need friction force. We're fighting friction, okay? Need friction force. The other thing to note here is that the applied force is not all of it's going to be going to acceleration, not even the horizontal part. But in other words, you're wasting a bit of effort by pushing upwards like that. Although it does reduce you're basically lifting the crate a little bit. These nuances, you don't have to see those ahead of time. You just can trust in the free body. But nevertheless, we just can't slam 680 newtons into the equation. If only it were that easy. It's not. Okay. Need friction force which opposes the acceleration force, or the applied force perhaps. Okay. Note on this one, we don't need to know the weight because I'm not trying to lift it. The one with the elevator was a different animal. That one, we were trying to move it vertically. And so the lifting tension in the cable had to overcome the weight of the elevator, and the residual was whatever was left over. Here, we're not trying to lift it. So weight and even the acceleration of gravity have nothing to do with this question because it's moving horizontally. We're not fighting gravity here. We're fighting friction. Need friction force, okay? Looks like this. The friction force opposes motion, okay? It's like this, right? The friction force is there. And you know, friction force is coefficient of friction times the normal force, okay? And I promised I'm not going to do a free body here. I didn't promise, but I alluded to that, okay? So the mu k is given 0.7. By the way, don't be presumptuous with the coefficient of friction. It's easy to realize, 0.7, 0.6, 0.5, whatever. You know, it's all small. No. You better make sure it's 0.7, because if it's actually 0.5, that's a significant change. 0.7 to 0.5, what is that? 20% less or something? That's a big 20% error. So even though it's a decimal, all right, don't just be cavalier about the friction force, the friction coefficient. Go test it. You learned how to test friction forces in statics, okay? Go and do a test and get the actual friction coefficient. All right? Anyways, here it is here, friction force, 0.7. The normal force is well, it's here's the force imbalance. The weight acts downwards, and the weight is 80 kilograms times 9.81. I know. I said it's not a function of gravity. Well, we have to make that into a force, okay? That's acting down, and then the y component of that, I'm getting the y force, eh? I'm getting the normal force is a y direction force. I'm doing a y summation here. Minus, okay, minus 8/17 of 680 newtons. Okay, the friction force, and so confirm you can do that. Right, the friction force is 325.4 newtons. I have it on another sheet, that's why I didn't calculate it, but so 325.4 newtons. This friction force is 325.4 newtons. All right. Now, We want the net force. It's not 680 minus that, because the 680, it's not horizontal. You need the horizontal component of that. So step 3, and boy oh boy, here's how, right? Need the horizontal component of friction. Maybe I'll call it residual. Not friction, of force. Okay, need the horizontal component of residual force. And now the analysis, this F delta T, M delta V. The force must, they're vectors. The force must be in the same direction as the velocity. It can't just be random. I mean, the extreme, you know, a vertical force and a horizontal velocity, well, you get nothing. Nothing happens. They don't go together. They have to be complementary directions. So I need the horizontal component of the residual force. Analysis must use complementary directions. Complementary directions on force and velocity. All right. So F net, I'll call it, is 15/17 of 680 newtons. That's the horizontal component of the applied force, right? That's the horizontal component of that. Of course, minus 325.4. And the net force available to create acceleration, which is really what's the cornerstone of kinetics, is that acceleration is occurring. The impulse momentum equation doesn't address acceleration directly, but it's one step away from Newton's second law. And you know, Newton's second law. Anyways, doesn't matter. It matters, but times 680 minus 325.4, 274.6 newtons to the right for acceleration. Okay. Finally, you get to apply the impulse momentum equation, okay? F delta T is M delta V. All right. The force applied, 274.6 newtons. The time of application of the force, 3 seconds. T initial is 0, T final is 3 seconds. The mass, don't overthink it. You're thinking, oh, I need to know the mass in the horizontal direction. Huh? There is no mass in horizontal direction. What? Mass is mass. It's not. It's independent. This impulse momentum method works in space. It doesn't matter. You remember Scotty, Star Trek, impulse power. You know, Kirk to Scotty, impulse power. Ah, cool, eh? Well, I'm not cool, but you know, impulse, whatever, cool. Anyways, 80 kilograms. Okay, final velocity unknown. And it does turn out to be you know, to say it's a one-liner is it's a one-liner. Well, not quite. There's a few lines there, and a couple lines there, and a couple lines. It's a 6 or 7-liner. But okay, velocity equals. Now I've shown the unit analysis, so I'm comfortable with this. 274.6. In other words, I'm comfortable with the answer being in units of meter per second. 10.30 meters per second to the right. Now that's haul and butt. The original question, 7 seconds. Look at it. Make that 7, eh? 274.6 times 7 divided by 80. 24 meters per second. And you think, well, that doesn't sound too fast. Well, that's 87 kilometers per hour. You've been pushing the crate across the warehouse floor at 87 kilometers per hour. Even 10.3 is crazy. That's across the room in 1 second, eh? Across a large room in 1 second. But anyways, that's the answer. Realistically, you wouldn't probably apply it for 3 seconds. I don't know what the scenario is for this. It's just a textbook question. But I find them kind of fun. But you know what? I don't have a life. So you, as a student, perhaps just have to get it done and get to the next milestone. So good luck to you. Don't act too fast on these questions. Reason them out. And remember, we need the residual force left after static equilibrium is achieved. In this case, equilibrium was applied force opposing or overcoming friction force. Okay. All right. You take care.